Okay, so here we go. Officially restarting. We are going over sections 14 and 15 today. So it's module 8 in Ivy Learn. We're just doing 2 sections and they kind of go together, which makes it a little bit nicer. So we have a quiz, we have our discussion board. I want to remind you to do the discussion board. About a little over half of the people did it last week, but discussion boards are 10% of your grade. Those are easy points. So make sure that you're getting that done over the course of the week so that you can get those easy points. So that if you miss something else, it doesn't hurt as bad because you've got a little bit of a buffer. I also want to take this time to remind you that Project 1, I believe, is due tomorrow. And those projects are also a little bit higher in percentages in terms of what they're worth in your grade. So if you haven't completed Project 1, you're going to want to get to that. And if you have any questions on that, let me know. I will check your Excel file. You just need to email that to me and make sure you get that done. So if you have questions, you know where to find me, but that is due tomorrow night at midnight. So, okay, section 14 starts with the normal distribution. And the normal distribution has a basic, what's the word I'm looking for? When you see normal distribution, you should think of what we call the bell-shaped curve. So this is kind of our basic visual representation of the normal distribution. And when we have this bell-shaped curve, there are some pieces that go with this. So if you would cut it exactly in half, so pretend that this is a perfectly drawn thing, right in the middle we have the mean. And the mean is noted by mu, which is this, it's a M. Some people think it looks like a U, but mu, MU, is the official name for that. So the mean falls directly in the middle. So 50% of the data falls to the left, 50% of the data falls to the right. All of the area under the curve adds up to 100%. And that should make sense because all of the area under the curve is, all means 100. So all of this adds up to 100%. We change colors for effect. It is symmetrical, as I mentioned, so this line of the mean puts 50% on this side and 50% on that side. Something else to just kind of think of. It's perfectly symmetrical. So if I put a line here and say there's 10% on this side of the blue line, in a symmetrical spot over here, there would be 10% on this line. So it's completely, totally symmetrical. And the area under the curve, not only is the total area 100%, but the area under the curve area refers to probability. So this is really where we're going to start getting into probability. I guess we answered a couple questions in section 13 about probability, the height of bars and that kind of thing. But the area under the curve is probability. That's going to be the basis of both of these sections, 14 and 15, is the area is probability. So that's kind of an overarching, there it is. But we also get into standard deviation. So we're going to say this is A and we're going to say this is B. So if I have this normal distribution curve and I have this normal distribution curve, so they're both symmetrical. You draw the line down the middle, there's the mean for both of these, but you can see these normal distribution curves look very differently. So like letter A, I would say that this is high and tight because it's tall and it's skinny, right? So high and tight is how I would, maybe reference that. But this means that it has a small standard deviation. Standard deviation is noted by the letter sigma, lowercase sigma. And I'm going to talk about standard deviation in just a moment. But the letter B, you can see how it's, I call it short and fat, right? It's really spread out. So this would have a larger standard deviation. And when we talk about small and large, it really depends on the data we're dealing with. But you can kind of get just an overall feeling for your standard deviation by the shape of your graphic. Now, standard deviation by itself talks about how spread out your data is, which kind of makes sense when we talk about these visuals, high and tight. If the data is all clustered around the mean, you have a small standard deviation because the data is not spread out. It's very clustered. Where in part B, it's all spread out, so we have a large standard deviation. So the standard deviation talks about the spread of data, basically. Okay, how far it is from the mean. Yeah, well, we're going to get into z-scores dealing with standard deviation, and that's what that talks about. Okay. So section 14 gets into the empirical rule. And the empirical rule is not difficult once you understand it. So the first thing I like to do is I like to do just a quick drawing about what is the empirical rule, where do these numbers come from. It's a little hard to do on a computer screen, but I've done it before and I will continue to do it. So I also like to, so the packet uses an example, but it's very abstract. They just use symbols. And I like to do an example with you with numbers because I don't know about you, but I work better with numbers. I don't do so well with symbols. I don't like the abstractness of symbols. So we are going to do an example where the mean is 70 and the standard deviation is 5. Okay, so we're going to do this example in this way. So the line in the middle will have a value of what? 70, exactly, because the mean goes in the middle, and that's always where we start. When we're talking about the empirical rule, we always talk about the mean first. Now, the empirical rule is also oftentimes called the 68, 95, 99.7% rule. Okay, so you kind of got to keep those numbers in your mind as well. So what this means is that 68% of all of our data will fall within one standard deviation of the mean. It's the first number, right? You can see these are in numerical order. 68 is the first number, so it's one standard deviation away. So if I go one standard deviation on each side, think about the horizontal as a number line. If I'm at 70 in the middle and I go to the right one place, what is the numerical value for that, the orange line on the right, if it's one standard deviation away? Think about a number line. As we move to the right, we would add. So we would add a standard deviation. 75, exactly. So we have the mean in the middle, and here is the mean plus the standard deviation. Now to the left, we're going to take the mean and we're going to subtract the standard deviation. So what would that value be? 65, exactly. So we would say 68% of our data falls between these two orange lines. Now remember what I said on that last screen before, that this is symmetrical. So this pink line cuts it in half. So from orange to orange, if this is 68%, how much falls in half of that? If orange to orange is 68 and the pink cuts it directly in half, how much is left on just half of it? 34, exactly. So this is 34% and this side is 34%. So you could say, let's pretend these are test scores in a class. So 34% of students tested between a 70 and a 75. That's what this means. Okay. Now we're going to continue on. I'm going to pick up the pace a little bit. 95 means we're 2 standard deviations away. So as I move to the right, now I'm the mean plus 2 standard deviations. Again, I'm just adding another standard deviation. So my value becomes 80. And on the left, I'm subtracting a standard deviation. So I have 60, right? This is mean minus 2 sigma. So from blue to blue is 95%. But remember, if you think blue to blue, so this is this whole piece here, is 95. But we have the orange in the middle. And the orange in the middle is 68. So if I take 95 minus 68, there's 27% left over not accounted for. That has to be split evenly between these two blue pieces. So if I take 27 divided by 2, I get 13.5%. And they give you this picture in your packet with all of these numbers, but they don't explain how the numbers get there. And I don't work well with material that I don't understand, which is why I like to do this it takes a few minutes, and then you kind of understand at least where the numbers come from. Okay, and then we go to 99.7. It's the third number, so we're 3 standard deviations away. So this is 85, mean plus 3 sigma. And over here we have 55, and that's mean minus 3 sigma. Same idea. Gray to gray is 99.7. But in between that, we have the blue, which is 95. So left over, there's 4.7% unaccounted for. It's symmetrical. So we divide that by 2, and we end up with 2.35%. And in terms of how this works with problems, again, we're talking about test scores. So 2.35% of students scored between an 80 and an 85. Okay. Now, the last piece is that the whole thing is 100%. And the whole thing is 100%. Gray to gray is 99.7. So we have 0.3% unaccounted for. Again, we divide it by 2, and that means that we have 0.15% in what we call the tails. And these tails are highly unusual. Because think about it, 0.15%, that is super, super small. So, super small. So those are unusual. And so from here, you could say, you know, the probability of somebody scoring higher than an 80. Well, higher than an 80 would be here to the right. So you would add those two together, it's 2.5%. Or what's the probability somebody scores lower than a 70? Well, here's 70, lower is this way, so it would be 50%. So you can add them together to get the different pieces that you want. And it depends, okay? So that's kind of the overarching how this works. And now we are going to do a problem, okay? Anybody have any questions on this particular I don't want to call it an example, it's more of just a show and tell. Okay. I do have a video that's just called The Empirical Rule that basically walks through exactly what I just did. So if it doesn't make sense and you want to watch that again, I think it's like 2.5 minutes long, and it just describes that. So, okay, let's go ahead and do an actual example. So we're going to do the 5 pieces. And it's going to be important that in part A that you draw it on your own, because as we move to the other questions, you're going to have the visual in front of you that you're going to reference. So the average miles per gallon in luxury cars is 29 with a standard deviation of 3. So first we're going to draw the normal distribution curve with all of our numbers on it, and then we're going to answer 4 probability questions about that figure. Right? That's what we're going to do. So just a refresher, the mean, right, average is 29, standard deviation of 3. Okay, so let's go ahead and draw the normal distribution curve. Oh, that was not a straight line, or even close to a straight line. Wowza. Okay, I want to give you guys about a minute, and I want to see if you can come up with this, okay? So I'm giving you a minute. Oh, I'm sorry. Yeah, the average, so the mean was 29, and the standard deviation was 3. That's definitely helpful to have. Okay. I'm going to go ahead and write the percentages in. I would recommend that you do this as well, just because it'll make the problem easier later. So these yellow numbers are all percents. You don't have to memorize these for the exam. Anything you need for the exam will either be on the formula sheet or given in the exam problems. But as you're doing your homework for this, you'd like to have them out at least somewhere so that you can see them. Okay, so where did you start when you did this problem? The mean, exactly. So we start with the yellow line, which is the mean. And then let's go ahead and go to the right. What are the numbers as we go to the right? The pink line on the right would be what? 32. The blue line, 35. And the orange line, 38. Very good. Okay, then we go to the left, which means we're subtracting. So we have 26, 23, and 20. Does anybody have any questions about that part of the problem? Okay, do you all have that written down? Because you're going to need that for the rest of the problems, and I guess I could just click onto the next problem and leave it there. Yeah, that'll work. Okay, so as we're moving on to the next problem, what is the probability a car gets less than 23 miles per gallon? When it says less than, which direction are we going to go? Less than means to the left. Exactly. And think about it. So here's 23 is here. If you want less, well, which way do the numbers get less? They get less going to the left. So for the part B, car gets less than 23 miles per gallon, you simply add all of those percentages to the left. So we're going to add 2.35 and 0.15. And together, what do we get? 2.5%. So there's a 2.5% chance that your car gets less than 23 miles per gallon. All right, then we go to letter C. What's probably the car gets more than 23? Well, more than means we're going to the right. So you're still at this starting point because we're still talking 23 miles per gallon, but now we're going to the right. There are two ways you can find this. What's one? Yep, so Amber has the idea of the complements. We know the whole thing is 100. So if the area to the left is 2.5, the area to the right is everything else. And that would give me 95.7%. That's the easiest way to do it. And the other way would be to add every one of these sections together. You get the same answer either way. So the probability of getting more than 23 miles per gallon is 97.5%. Okay. All right, stop me if you have questions. What's the probability a car gets between 20 and 32? Okay, so recognize. Where is 20? 20 is here. Where is 32? It's here. So how do I find the probability between that? If we're going purple to purple, how do I find that space in between? Yeah, Stacy, exactly. You just add those numbers together. So all of the numbers that fall between purple and purple, 2.35, 13.5, 34 plus 34. If I add those together, that's going to give me the probability between those two values. What do you get when you add those four numbers together? 83.85%. Yep. I know my screen's getting a little full of crap, but hopefully you're following along. Right? So you can see the math inside this section is not difficult. You all can add and subtract. I feel very confident about that. It's knowing where the numbers lie and what they're asking for. That's the hard part. But the math itself is not difficult. It's the wording. So very similar. Oh, wrong class. Different class. It's all about wording. The math isn't what gets people. It's the wording and knowing what they're asking for that gets people. Okay, we've got one more question to go with this one. How likely is it that a car gets more than 38 miles per gallon? Well, let me get a color here. Okay, so here's 38. Which way is more? To the right. So we're looking to the right of 38, which gives me an answer of 0.15%. And that's how we can use the empirical rule. And that's pretty much what your homework is going to look like. I think you might have to use Excel a little bit for that. I think you will never have to find standard deviation by hand. Okay, but you will maybe need to use Excel to find standard deviation. I'll talk about that when I get a clear screen here. But this is the basic of section 14 and how it's going to look. Now, I would like to then have just a 2-second conversation here of, can you see any limitations of the empirical rule? Even just talking about this example with gasoline and miles per gallon, do you see any limitations? And feel free to use your microphone if you'd like to talk. It might be easier than typing a bunch of stuff in. Nobody sees any limitations? You think this is the perfect approach? Okay, I'm guessing most of you, if not all of you, have at least one car. Do your cars get these miles of gallon exactly? Does everybody's car get it? Okay, so my Jeep gets less than 20. Okay, so your number's not on here. 2 cars are different. Absolutely. Every car is different. Yeah. So my car tells me how many mpgs I'm averaging on that tank of gas. And usually there's a decimal involved, right? Like it's on the way here, it was like 36.8. Well, that's not on here. So if I wanted to know what's the probability that a car gets more than, my car's not a luxury car, but the probability my car gets more than 36.8 miles per gallon. Well, 36.8 isn't on here. 36.8 falls about right here. That doesn't tell me anything. So the limitation of the empirical rule is that you are locked in to 7 data points, right? The mean and 3 standard deviations on each side, and that's it. Anything in between those values, you have to round. So if we were talking about my car at 36.8 miles per gallon, I would have to either round down to 35 or round up to 38. But neither one of those is accurate. 36.8 is the miles per gallon. So that's where the empirical rule has its biggest limitation, is that you have to do a lot of rounding to even start. And then all of these values under the curve, these are all estimates. So not only are you rounding to get the value at the bottom, but then you're estimating the probability inside. So you can see how this is like, it's a great theory. It's very good for estimating very quickly, because you can see how easy it would be to, 36 is close to 35. I want more than that. Add those 2, done, right? You can do the problem in 2 minutes once you know what's going on, but how accurate is it? And so that's where we lead into section 15, where we do these same type of problems, but we use a more accurate method. Okay, so section 14 is the estimated method that once you understand is quick and easy, but how accurate is it? Who knows? Okay, so let me erase this. When I talk about standard deviation in Excel, you're going to go to your formulas, right? So formulas, and then you're going to go to statistical, just like you have been with section 8 and all of those formulas. And then you're going to go to stat dev, standard deviation, .s. And it's going to be important that you use S for your standard deviation. S talks about sample, and sample, because you're never going to talk to everybody, right? That's impossible. Talking to everybody as a population, it just doesn't happen. So you want to use StatDevS. So any of your web work assignments that talk about go to Excel and find your mean, your standard deviation of this data. So you'd go to Excel, you type in the data, use your formula for mean, or your average formula, and then you're going to use your StatDevS to find your standard deviation. Then you can create the normal distribution curve and type in your numbers, and it'll go from there. Okay? Of course, if you have questions, all you have to do is email me. All right, so now we're getting into z-scores. So z-scores, again, so we're taking section 14 and we're going to put it into a more accurate method so that we could find 36.8 miles per gallon if we wanted to. So a z-score is simply a way to change data into a standardized form. So if you think about it, if you're talking about cars, you have average miles per gallon, and that would have a mean and a standard deviation. And then maybe you're talking about exam scores, and you would have a mean and a standard deviation. And then we're talking about the average number of times I trip over my own feet in a year, and that has a mean and a standard deviation. And so we have all of this data, and they all have means and standard deviations, but they're all drastically different. Right? So there's no real way to have a uniform way of doing this math because everything is so different. So z-scores are a way to take any random data that has a mean and a standard deviation and turn it into a z, a value of z, which just means we're putting it into a common numerical form that allows us then to find probability. And that is the goal of a z-score. So the z-score, by definition, the z-score is the number of standard deviations away from the mean. So numerically, just real quick, if we know the mean is 70 and the standard deviation is 75, not 75, goodness gracious, I'm ahead of myself, and the standard deviation is 5, similar to our empirical rule problem we did earlier. If I said we have a value of 80, I'm using easy numbers on purpose. Well, think about it. If the mean is 70, standard deviation is 5, and my value is 80, 80 is 2 standard deviations above the mean, right? Because 5 plus 5 is 10. So this would have a z-score of 2 because it is 2 standard deviations above the mean. Positive z-score means it's higher than the mean. If I would have a value of 60, 60 is lower than the mean. Again, by 10, 10 is 2 standard deviations, so this z-score would be -2 because it's 2 standard deviations below the mean. So a z-score that is negative implies it is less than the mean. Okay, and don't worry, we're going to play more with z-scores so that you can kind of get a better feel for this. So there is a formula, because you don't have to do all of this, in your head. There is a formula for z-scores, and the formula is on your yellow sheet. So if you don't have your yellow sheet out, go ahead and get that out, because that will be helpful in this here problem. So page 246 is the yellow sheet that's in question for today. At the top of page 246, you will notice that there is a big table, a z-score and probability, and that is what we are going to be playing with today. Right underneath that table on the left, you see the formula z equals x minus mu over sigma. And that is the formula that we are going to use in order to find z-scores. So just to put that into words for you, the x is the value, right? It's the data point in question. Mu, as we know, is the mean, and sigma, our denominator, is the standard deviation. Now, depending on your calculator, you may want to put your numerator in parentheses first, especially if you're going to put all of this in at one time. It's going to be important that you subtract the numerator first before you divide by the standard deviation. That is super important. Okay, now, as we get into the table, the one thing I need you to remember about the table is that it always gives you area, I can't type, or spell for that matter, it always gives you area to the left, right? So we have our normal distribution curve. That doesn't change. But if I say, hey, we have we have a z-score of negative 1.3. Okay, so for right now, I'm just telling you that. Z-score of negative 1.3. Look at your yellow sheet. Find a z-score, right? So within each of those columns, z-scores are on the left. So find the z-score of negative 1.3. What do you see on the table next to the z-score value of negative 1.3? You do see the probability. Yes, Stacy, can you give me a numerical value? Oh, there we go, 0.0968. So that is the probability to the left. So the table gives you 0.968. So whatever we're finding, if we needed the area to the left, it's 0.0968. Now you can change that to a percent from there if you would like. Multiply by 100%. But think about this. If area to the left is 0.0968, how do I find area to the right? Right idea, Amber. Yes. Think about what we did with the empirical rule, right? We subtracted from 100%. Well, now when we're using the probability table, we're dealing with decimals. So what is 100% as a decimal? The whole thing is just 1. Exactly. So if we would take 1 minus 0.0968, that gives me the area to the right, which is 0.9032. So you have to remember, the table gives you area to the left. You then can subtract from 1 to find area to the right. Okay. But in order to use the table, you have to have a z-score. So when you're trying to find probability, sometimes you have to find the z-score first in order to use the probability table. So, okay, let's go ahead and do some math here now that I'm yapping all over the place. So we're going to use the idea that the average calories burnt at the gym is 460 with a standard deviation of 35. And of course, this is completely made up data. So the first thing we're going to do, part A, is we're just going to find the z-score of somebody who burnt 510 calories. Right? And when they're asking for a z-score, they're really just saying, how many standard deviations away from the mean are you? If your value is 510, how many standard deviations away are you? That's what a z-score is. All right, so we are going to use our formula, z equals x minus mu over standard deviation. So you are given 3 numbers. You have to determine where they fit in this formula. So does anybody have an idea of what the value is? What's going to come first in this formula? $5.10. Yep. I mean, if you can locate the mean and the standard deviation, the value is the other one. So 510, what am I subtracting? What's the mean? 460. And the standard deviation. 35. So depending on how you're typing this into your calculator, again, you may want to put your numerator in parentheses. And think about it. If the average is 460 and I'm doing 510, I'm better than the mean, right? I'm higher than the mean. So my z-score should be positive. Those are the kind of things that you can kind of think through as you're looking at these problems. So can anybody give me my z-score for this particular problem? I did not get 1.67. Yes, Stacy, I will go with that. So 1.428. Now, if we were in a statistics class, we would have a z-score probability table that's like 2 full pages. Well, we don't, right? We have a z-score table that is half of 1 page, and therefore we're going to have to round. So if you look at our z-score of 1.428, and then you look at the z-scores on our yellow sheet, what is the closest z-score we have? 1.4, exactly. So for this example, if you burn a 510 calories, you will have a z-score of 1.4. And that's, so if you think about your normal distribution curve, you know the mean is in the middle. Well, 1.4 is bigger than the mean, so a z-score of 1.4 is going to be somewhere over here. And I do recommend, especially if you're a visual learner, to go ahead and make a quick sketch of these normal distribution curves. It'll make the problems easier because then you can shade in. Are you trying to find lower than that, higher than that? Then you can shade whichever side you want. It'll make your life a little easier. Okay, let's do the next one, which is we're going to add on to this. So now it says, what is the probability of someone burning less than 510 calories? Well, generally, if this is the problem that you're reading, you say, okay, probability of burning less than 510 calories. The first thing I need to do is find a z-score, right? And we did that. We took 510 minus 460, we divided by 35, and we have a z-score of 1.4. So if my z-score is 1.4, if I want to burn less than 510 calories, which direction do I want to find, left or right? Left, exactly, because less is left. And so that makes it easy. If I want left, then I simply have to go to my table, find 1.4 in the z-score, and what is the area to the left of that? Very good. 0.9192. So if you find this, this is in the fourth column to the right, fourth one down, z-score of 1.4, you just look directly across from that, and the probability is 0.9192. And that's area to the left. So the probability of somebody burning less than that is 91.92%. You can change that to a percent. Now, if we go to the next problem, look at that, circles in the same spot. Whoop, whoop. Now we want to know what's probably somebody burning more than 510 calories. So again, 510, we need to find a z-score. It's 1.4. But if I want more, now I'm finding area to the right. So how do I find that pink area on the right? Exactly. 1 minus 0.9192, which gives me a probability of 0.0808. So just a shade over 8% chance that somebody will burn more than 510 calories. Okay. Questions on finding the z-score or either of the probabilities in this particular question? Okay, I'd like you guys to try one. Number 10, average calories burned at the gym is 460, excuse me, with a standard deviation of 35. What's probably if somebody burns less than 400 calories? I'm going to give you a few minutes. When you have it, I would like you to just type yes in the chat box, and then we'll go through kind of the math together in a minute. But I'm going to give you a few minutes, see what you can do. So type yes in the chat box when you're done. Okay, what was your first step? There you go. We got to find the z-score. So you recognize that you want to find probability, but there's no real way to do that without a z-score. Even if you would do the empirical rule and type, draw your curve and put your numbers in, 400 is not on there. And if it's not on there, you can't use the empirical rule. Okay, so we start with our z-score. So x minus the mean over the standard deviation. So what z-score did you use? Tricia says negative 1.7. I like it. Okay, so then you say, okay, here's my picture. Negative 1.7, right? The mean is in the middle. Negative is to the left of the mean. So here's my z-score. Are you finding the area to the left or the right of that negative 1.7? Left, exactly, because it's burning less than 400 calories. So we want this. So we go to our table. And what does the table spit out for that probability? Yeah, 0.0446. So there's a 4.46% chance that somebody will burn less than 400 calories at the gym. There's the problem. Okay. Questions, comments, concerns, suggestions. Right. And then remember, to find the area on this side, all of this over here, we would just take 1 minus 0.0446, and we would get 0.9554, and that's the area greater than 1.7 or more than 400 calories at the gym. Okay. All right. The next problem we are going to do together, because it's a little bit different, and I don't want you to be confused. So this is the last problem of the day, unless you have other questions. So the average calories burned at the gym, we're going to stay with this because it's easy. But what is probably somebody burns between 440 and 500 calories? Now, if you think of this pictorially, 440 is less than the mean, so it's going to be somewhere over here. 500 is more than the mean, so it's going to be somewhere over here. We want to know this area. We haven't done that yet today. We've either found less or more, but never in between. Okay, so does anybody have any idea what we would do first? Z-score for each. Absolutely. You can't do anything with probability unless, well, in this case, unless you have a z-score. Okay, so we need to find a z-score for 440. Pretend that's a minus sign. And we need to find a z-score for 500. Okay, so go ahead and compute those. And go ahead, whenever you have them, just go ahead and put them in the chat box. Okay, I'm going to agree with the 1.1, but when you get to the z-scores that are between, that have the 0 in front of them, you get, okay, so for this one, it comes out to be roughly negative 0.57, right? Oh, I see what you did. You rounded up to negative 0.6. I got you. Okay, well, 0.57 isn't on there, so you either have to go to negative 0.55 or negative 0.6. Which way are you going to go? And so, Tricia, this kind of answers your question. It's really closest to. That's really what, in this particular case, you should pick closest to. So 0.57 is closest to which one? 0.55 or 0.6? It's closest to 0.55. Now, Amber, if you used negative 0.6 like on the exam, obviously your answer would be different than mine, or different than the question in the test. But if you have this, worked out on your scrap paper, and I can see that and say, oh, well, she rounded to 0.6 instead of 0.55, I would give you full credit for that, because mathematically you knew exactly what you were supposed to do. You just rounded the other direction. There's nothing wrong with that. So that's just make sure that you show your work on your scrap paper so that I can make sure to give you the credit where you deserve it when it comes to the test. Okay, for this example, we're going to go ahead and use 0.55 because that's what my answer key has. So that's what we're going to use. Okay, so we have our z-scores. Now, I want to diagram this for you, if you will. So this 0.55, we're going to use blue to recognize negative 0.55. If I use the probability table, it's going to give me all of this area to the left. Then, still thinking, I'm going to use yellow to represent 1.1. If I look at 1.1 on that, that's going to give me all this area to the left. Well, remember, we only want this area in between. So knowing how we can get the probability from the table of area to the left, do you have any idea how we can work these numbers so that we only have the area in the green? Any ideas? Subtract, absolutely. Think about it. We know, let me go back to blue, area to the left of negative 0.55 is 0.2912. Right? That's all of this area to the left. I don't want any of that area. That's not in the green at all. And then when I go to yellow, area to the left of 1.1 is 0.8643. Well, part of the yellow is in the green, but the rest of it is with the blue. So if I say, oh, I got to get the right color here. Everything to this side, if I would subtract them, the yellow line minus the blue line, this is the part that goes away because that's the overlap, right? When you subtract, it's the overlap that goes away. So I would simply need to take 0.8643 and subtract 0.9212, and the leftover is the stuff that's actually in the middle where I want. So what do I get? 1, 3, 7. I carried, so I end up with a 5. So 0.5731 would be the area in the middle here. Okay, that's about the hardest type of a problem you're going to have in section 15, is where you have to, subtract the two probabilities in order to find the area between two values. So, okay, that's section 15. Do any of you have any questions over sections 14 or 15? The empirical rule or z-scores, or probability, anything else? Any questions at all relating to Math 123 at this point? All right, we're getting to crunch time. We're about well, this is technically module 8, so this is the halfway point in the class in terms of material for you guys. Exam 2 will be here in 2 weeks. So if you haven't scheduled exam 2, that is the week of the 14th. 14th being that Saturday. So the week before that, I think Monday is the 9th, maybe. That's the week that you're going to want to be scheduling your exam. Of course, if you have questions, you can let me know. So we'll be finishing Unit 2 next week in this session. Okay. If you don't have any other questions, then I'm done for the day. So you guys can go off and do math. Get your discussion board completed. Starting your homework early. So if you have questions, I can help you. And yeah. Get your project 1 done. If you do not have project 1 done, it's due tomorrow, and it's a large portion of your grade. So get that done. So okay, I'm done. If you have no other questions, go off and prosper, and I will see you next week. You know where to find me if you need me. Thanks, guys.